this. Okay, so we have a lot of different types of waves. We have waves in water, like water waves. We have sound waves, and that's what we'll be talking about in this chapter. We can have other types of mechanical waves as well. Mechanical waves, including things like waves on a rope, on a spring, I don't know, a whole bunch of different types of waves. The thing that defines a wave is that they are periodic. That means that they repeat. And we'll call these then periodic waves, because they repeat. Sound waves are periodic as well. That means that as it travels through space, you're going to get a repetition of one piece. It's going to repeat one after the other, one after the other. I'll show you what I mean by that. Now we have two different types of waves when we're talking about waves. We have transverse waves and longitudinal waves. And those two different types of waves describe what they do to the medium. So a transverse wave transverse waves, these make the medium move up and down. So a lot of these waves that we listed up there, the mechanical waves and what have you, those are transverse waves. You ever do the wave like at a football game or whatever? That's a transverse wave. You want to do it? See, it's like y'all are the medium. And when I come, I'm going to be like a silly. Woo-hoo! All right? And when I walk in front of you, you raise your hands. Y'all ready? All right, go. See, so this is a come on, get into it. This is a transverse wave, right? And the medium then is moving up and down. Now, on the other hand, a longitudinal wave, a medium doesn't move up and down. In a longitudinal wave, the medium will move side to side. So I like to think of this as like a hugging wave. So now when I walk past the room, so you're going to reach over and hug the person in the aisle next to you. Yes. Okay? This is like a longitudinal wave. Instead of the medium moving up and down, you're going to lean towards one another and you're going to embrace the person next to you. In a very long embrace. Okay? Are y'all ready? Okay. Let's do it. Yeah, so here we have our medium will move together, and then when I move away, you move apart. So that's like a hugging wave, if you will, as opposed to the wave like you do at a football game. In a longitudinal wave, then, they make the medium move side to side. It's like a hugging wave. Sound waves are longitudinal. So sound waves don't make the medium move up and down. They make the medium move close together and then move far apart. These are sometimes called pressure waves. Or they're sometimes called compressional waves. And the reason is that if you think of sound, when you see a sound wave like in space, you have an area of high pressure and followed by an area of low pressure, followed by an area of high pressure, low pressure. So this is a high pressure, this is a low pressure, this is a high pressure, this is a low pressure. And so we'll see with the ear that the ear has this membrane. When that high pressure impinges upon it, it pushes it, which causes you to push on those little bones in your ear, which cause you to create an electrical signal. We'll talk about all that jazz, okay? So it is a pressure wave or a compressional wave. Simple harmonic motion is related to waves. In fact, waves are a type of simple harmonic motion. This is just a type of motion where something oscillates due to with a force. That is proportional to the displacement from an equilibrium position. I'm going to abbreviate this equilibrium position. So when we think about this, a good example of simple harmonic motion, a lot of y'all did the lab last semester. But by the way, for the lab, I know, well, y'all all have the lab, but just want to remind you that registration is opening up. I think a lot of you should have already registered. Am I right about that? So I think it's like sophomores today. All right. Yeah, so hopefully you've all registered. I think that everybody in here has had the lab, but if you're not, just let me know, okay? They're starting to fill up, as you know they do. But if you need help with that, come see me, okay? I'm pretty sure we've gotten everybody in this room. Okay. Anyway, a good example of simple harmonic motion is a mass on a spring. We had a lab like this last semester, where you have this mass on a spring. The more you stretch the spring, the larger the force is. That's called Hooke's law. F is equal to kx. And so if I increase the displacement x from my equilibrium position, then I get a larger force. So that is simple harmonic motion. The same is true for sound. It's a type of simple harmonic motion. If you think about this pressure wave, if I take a molecule of gas or liquid or whatever, and I move it out of its position, there's going to be a force that's wanting to put that molecule back in its original position. We'll talk about that in terms of elasticity and how that affects the travel of sound. But the same thing happens with a mass on a spring as happens in a compressional wave for sound, that I'm getting the displacement of my medium from its original position, and there's a force that wants to take it back to that original position. All right? Sound is also then simple harmonic motion. I wanted to show you all a video. This is sort of related. It's kind of interesting, where he's looking at a spring and how a slinky, when you drop it, what happens to it. So let's watch this video. It's about 4 or 5 minutes. They talk about in like my area, which is in star formation, a sound speed, so that when you have a star that's forming, this is just sort of for your own information, don't write this down, but when you have a star that's forming, you have material that collapses on to it, and you get collapse that begins in the middle, but you don't really get collapse on the end until you have a certain amount of time that's passed, while that information that collapse has begun in the middle travels to the outer reaches of your cloud. And they call that the sound speed. And it's sort of like with the slinky. It's like the top of the slinky doesn't know it's falling until, or rather the bottom of the slinky doesn't know it's falling until the top reaches it. We call that the sound speed. It's a lot like what we're talking about in this class about the actual sound speed, but we also talk about it in terms of like a rate of transferring information. Like when does the top of the slinky reach the bottom of the slinky? Anyway, it's kind of an interesting thing. Try it out if you have a slinky at home. You can sort of see that it falls first, but it's sort of hard to see also. But anyway, let's see. So sound is an example of simple harmonic motion. The restoring force for sound, because with simple harmonic motion, you have to have this restoring force causing it to go back into its equilibrium position. And the restoring force for the sound then is the pressure of the surrounding medium. Oh, I'm sorry, surrounding medium. So again, if you imagine that you have these atoms, they're all arranged just so, and then you have this wave that comes through. It's going to cause one of these atoms to move out of its position when this wave comes through, and then there will be a force that causes that atom to go back into its position. That is dependent upon the actual medium that you have. All right. We want to define a few things about waves. We've already seen this some, and you've probably seen this in other classes. So first I want to show you two different types of graphs that we can have for waves. They look a lot the same. In fact, they look identical, but they give us different information. So both of these graphs, we'll be looking at periodic waves, and we'll be looking at graphs like this. This is a snapshot graph, and then this is going to be a history graph. Notice the difference in these is what's on the x-axis. Here I have position, and here I have time. The snapshot graph says, what if I were to just take a picture of the wave at a particular point in time? That's what it means by snapshot. I'm taking a picture of the wave at a particular point in time. So this is at time 2.4 seconds or whatever. And then from this, we can figure out a couple different things. We can find the amplitude of the wave. The amplitude is here. It's the distance from our equilibrium position to either a peak or a trough. So this is our amplitude. And then our equilibrium position is there. We also need to define our period and our frequency. Both of those are related to, we can also find our wavelength as well, I'm sorry. So our wavelength is the distance for one full oscillation. So one wavelength goes from here, goes through one full cycle of the wave, and over here. So this is one wavelength. Notice though that you can measure wavelengths from different points. So say for example I started here, I would go through one full oscillation over to here. So this also is one wavelength. I can measure it from any different point. So if I started here, my wavelength would go from here over to here. If I started here, it would go over to here. Notice that when you're doing it in the middle of the wave of this snapshot graph, that you jump over one of the things because you complete a full cycle of the wave. So a full cycle of the wave is a wavelength like that. That is one full wavelength when I go through one full cycle of the wave. From the history graph, this shows how the wave changes through time. So it takes one particular position and one position in space and asks what happens with that position through time. So I pick one space, say on a water wave, and that point moves up and down, up and down. And so that gives us our history graph. From this we can get a couple different things. We can get our period, t. T is the time for the wave to travel one full oscillation. Or one wavelength. That period on our history graph goes from here to here. Notice that looks the same as our wavelength. It's because the period is the time for one wavelength. Also our frequency, as you probably know. How is our frequency related to the period? That's a question. It's 1 over the period, right? So the frequency, you should have had this in, gosh, I hope in high school, but if not, maybe in chemistry. But anyway, our frequency is 1 over the period. We measure this in hertz. It has units of inverse seconds, and 1 inverse second is equal to 1 hertz. We also have the speed. The wave speed is based on these. The wave speed v is equal to our frequency times our wavelength. Or if you want to think of this, our period t is our time for one full oscillation. So you can also think of this as this is our wavelength divided by our period. Because the wave travels through one wavelength in one period. But 1 over period is just our frequency. So these two terms are equivalent. All right. So you'll need to know this, and you'll need to know this. This will be on your equation sheet. I don't think it's on there right now, but I'll update it. Let me see if that's the case. No, it doesn't look like it's on there, but I will put it on there, and I'll put it on Moodle for you. I'll update your equation sheet. There are a handful of equations that you'll need to to be aware of, and I'll put those on there. These are ones that will be on there. The wave speed and the frequency will both, will both be on there. Let's see, let's try a few of these little quick test questions. I have 4 here. Let's do this one right now. Which of these shows the wavelength of this transverse wave? Is it A, B, C, or D? I'll zoom in a little bit, but you should have it in your book as well. Which of these shows the wavelength of this transverse wave? A, B, C, or D? And what type of graph is this then? Is this a snapshot or is it a history graph? It's a snapshot, right. If I'm measuring wavelength, I'm measuring a distance, and that would be our snapshot graph. I got some new jokes, so y'all better do well. Have some good ones to go. All right, I'll stop at 108. 108. Okay, good. B is right. It's for one full oscillation. See, a lot of y'all, some of you put C. Well, B, I start right here, and I go through to here. That is B. C has gone a little bit too far. So if you want to check this, I always like to think, okay, right here, I'm going up. I need to be at the same position where I'm also going up in the same way. And then that will signify to me that I've made one full oscillation. Let's try this one over here. Which of these has the higher frequency, A, B, or C? Or do they all have the same frequency? And by the way, these are history graphs, not snapshots. Because if I'm looking for time information, I need to know the history, not the snapshot. All right, we'll stop at 45 seconds, 45. Okay, good. A is right. A has the higher frequency. You can think about this a couple of different ways. First of all, the frequency, I didn't say this, but the frequency is the number of peaks in a given time. And so this is the shortest time, and yet I have the same number of peaks. And here I have the same number of peaks in a longer time. So A has the higher frequency. Or you can think about this in terms of F equals 1 over T. The one with the higher frequency has the shorter period. So if T goes down, that means F goes up. So here, my period is the time from here to here. That's a shorter time than, say, the time from here to here, or the time from here to here. So the one with the shorter period has the higher frequency. The smaller period has the higher frequency. What did Batman say to Robin just before they got in the car? Get in the car. Well, that was funny. During a time of one period, a wave travels what? All right, just about 5 more seconds. I'll stop at 28. Okay, awesome. B is right. During a time of one period, a wave travels one wavelength. So there's no those basic definitions for what is wavelength, what is frequency, and what have you. And then finally, sound is what type of wave? Oh, let's see. Why did the... Well, I'll give it to you after this one. I'll stop at 25. 25. Sound is what type of wave? Awesome, C. It is a compressional wave. Or it could also be called a longitudinal wave. Or it could also be called a pressure wave. All of those would be appropriate terms for a sound wave. All right? Why did the tomato turn red? Because he saw the salad dressing. Okay. All right, let's look at sound of a vibrating string. And this will come back because we're going to look at resonances. And we'll see how we create resonances in tubes, closed and open tubes, and then also on strings. But we're just going to look sort of now at how the frequency of the sound is affected. In musical instruments, the larger instrument is usually, well, what is it? What is it usually in frequency? Is it usually have a higher frequency, or does it usually have a lower frequency? Right, a larger instrument usually has a lower frequency. So, for example, the tuba, which I used to play, has a very low frequency as opposed to the piccolo, which, you ever seen a piccolo? They're itty bitty, right? They're like this big. It plays a higher register, or in the treble clef. So usually a larger instrument is lower in frequency. By the way, that's why men typically have lower voices, because their vocal cavity, their neck and all that is longer usually and bigger, and so it just resonates at a lower frequency. You also see that with guitars, or say a bass guitar versus just a 6-string guitar, whatever. That the bass guitar is quite a bit bigger than a regular guitar. The strings are longer. The strings are also just thicker. The vibrating string, the frequency is given by this. For any vibrating string, it's given by 1 over 2L times the square root of T over mu. And here L is the length of the string. T is the tension in the string. And mu is something called the mass density. All right, so anybody play guitar or some sort of stringed instrument? Yeah, there are a couple different ways, right, that you can get a different frequency on a guitar. So on a guitar, one way to get a lower frequency is just to make the string thicker. If you give it a higher mass density, a higher mu, you make this number bigger, and that makes the frequency go down. So if you increase the mass density of your string, it causes the frequency to lower. That's why bass guitars have much bigger strings than a 6-string guitar. Also, you can increase the tension, and so if you've ever tuned any kind of string instrument, you have those keys up at the top of the neck or whatever, the neck. Yes, the neck. If you increase the tension in the string, it causes the frequency to go up. Okay? So you can adjust the tension and the mass density to change the frequency, and then of course, as we've already talked about, if you have longer strings, and that will cause for a bigger, or excuse me, a lower frequency. Have you ever done this trick for y'all? This really blows my kids away. You want to hear it? Low, high, low, high. Can y'all do that? Try it. It's not as easy as it sounds. Go ahead. Try it when you leave today, when you're not afraid of being embarrassed. But it's not as easy. It takes lots of practice to do that. Okay. Let's do a few more clicker questions. You do not have these, unfortunately. I will post them. Actually, let's hold off. We'll hold off on these because we have to wrap up soon anyway to do evals, and so I'll just post these on Moodle. That way you can print them if you like. I'm sorry, I didn't have them. I just put them together, so you don't have them in the back of your book. But I'll post them on Moodle or on the website actually and send you the link. and then you can print them, because I know a lot of you like to take notes, and I recommend that you do that. So I'll just wait, and we'll do those. We'll catch up with those next time. But let's look at the speed of sound. The speed of a wave doesn't depend either on the pitch or the loudness. Well, first of all, let me let's talk about sound. We have pitch, and we have volume, or loudness. The pitch is dependent upon the frequency, and the loudness or the volume is dependent upon the amplitude. All right, so remember this. If I'm looking at my history graph, my frequency is the inverse of the period. Remember, our period is from here to here. That's my period, and my frequency is 1 over that. And then my amplitude, which I can also get from the history graph, my amplitude is this value. That's my amplitude. And the volume is given by that amplitude, or it's related to the amplitude. But the speed of a wave, it turns out, doesn't depend on either the frequency or the amplitude, on the pitch or the volume. So if you speak more loudly, that doesn't mean that the sound will reach the person faster, or if you speak at a higher frequency, it doesn't depend. It only depends on the medium. And that is the only way that you can change the speed of a wave. So a high-pitched noise will not have a higher speed. So the speed depends on the well, we'll come back to this stuff. So you might think, well, gosh, if I look at this, which you just gave me, the V is equal to lambda times F, it does seem like the frequency and the speed are related, right? Because if I make the frequency increase, then you would say, well, that would make the speed increase. But that's not the case. The speed is always constant, depending upon your medium. So, in fact, if I change my frequency, it doesn't change the speed, it only changes the wavelength. Okay? So, the frequency does not affect the speed, it only affects the wavelength. If I change my frequency, then that changes the wavelength, and vice versa. It doesn't affect the speed. The speed depends on the elasticity of the medium. More elasticity, or a more elastic medium, then you have a higher speed. As we move from one medium to another, say we move from gas to a liquid to a solid, as I move to these, I'm moving in direction of increasing elasticity. This elasticity, I'm not going to use this variable, but the elasticity is usually given by the Greek letter beta. But I'm not going to use it. We're not going to deal with it. I just want you to know that the speed does depend upon the elasticity, and that solid materials have an elasticity that's quite a bit higher than liquids or gases. What the elasticity measures is the elasticity measures the force, or the restoring force, or it's related to the restoring force on the atoms in the material. So if I have more restoring force, that is, if I have a higher force forcing that molecule or atom back into its position, then I'll have a bigger elasticity. So, you think about a piece of steel block, those molecules or those atoms in steel have a much higher restoring force than, say, in a gas. Because if I move the gas around in this room, it's not really going to go back to its position because it has a very low restoring force. But if I have something in a solid, for example, or a crystal type structure, that has a very high restoring force because it's going to be forced back into its position. That's why they are what they are, being a gas, a liquid, or a solid. So the result of this is that sound will travel a lot faster in in liquids or gases. So, for example, in air, sound travels about 340 meters per second. It travels about 1,500 meters per second in water, and it travels something like 6,000 meters per second, a lot faster, a factor of what, 20 times faster in steel. And that's all based on the elasticity, that the elasticity in those solids and liquids are higher than they are in gases. You can try next time you go to the pool, right, that the sound will travel at a much faster rate than it would in air. All right, let's try these questions. And then we will stop after these. I need to do evals. So think about who wants to take the evals to the dean's office for me. I'd really appreciate it. All right. We're looking at this one on the left. Which medium is the most elastic? I'll stop at 25 or 28. Okay, awesome. The solid is more elastic. Solids and then liquids follow, and then gases follow after that. And now let's try B, or excuse me, this one. The answer here was A. The speed of a wave depends on which of these: the frequency, the wavelength, or the medium, or some combination of those. There it is. All right, just a few more seconds. C is right. The wave speed is only dependent upon the medium. Okay, so we need to do evals for this class. Listen, the evals are pretty important. They're not really going to impact you, but they will impact students in the coming semesters. And always take the evals, and I'll go through them after I get them and sort of think about what are things that I can change in the class. So I really appreciate any sort of critical feedback that you have. There are a couple of different things that you need to fill out. We have about 15 minutes, or 2 minutes. First of all, I need somebody that's willing to take them to the dean's office. They're giving you 2 different forms. The one that Ryan is handing out are open comments. Those come straight back to me. So whatever you write on there, it comes straight back to me. They sit up in an envelope. I get it, after grades are turned in. And then the bubble form has things that you bubble in, and that goes to the administration. They look at it. I look at the numbers too. They are useful. So take some time. We have 10 minutes to fill it out. That should be plenty of time. You'll need to put the CCN number on there. The CCN for this class, the identification number is 10657. Does anybody need a pencil? I have a few if you need to borrow one. I need a pencil. You do have to do it with a pencil. All right. Any questions? Somebody take it to the dean's office. Am I willing? Goes to the college office over in Pelcher Hall. You do it, Emily? Oh, okay. Emily, you got it? Okay. I'll be out here in just a second.